The second alkyl halide reaction is the beta elimination. The second alkyl halide reaction is the beta elimination. In this reaction, two adjacent carbons, one of them will have a halide, the other one will have a hydrogen. So you need a hydrogen on the carbon adjacent to the carbon that has the halogen. That's the beta carbon, by the way. The carbon that has the halogen is called the alpha carbon. If we have a base that can pull off the proton, we can make the alkene. So we pull off the proton, the electrons between the carbon and the hydrogen, they go to make the pi bond. As the pi bond is being made, the halide comes off. So, by the way, that was one mechanism that can happen. There are two mechanisms, just like for substitution reaction. There are two mechanisms for this kind of reaction. One of them is concerted, which is the one I just described, and the other one is stepwise, in which the halide is lost first to make a carbocation. That's exactly the same step as the first step in the SN1 substitution. So we make the carbocation. Then once we make the carbocation, it's very easy to take off the proton on the carbon next door to the carbocation in order to make the pi bond. So we're going to talk about those next. As we think about the products that one can make, sometimes there are more than one. We want to make the product that makes the more stable alkene, and the more stable alkene is more substituted. So let's look at this first reaction scheme that's shown above, 2-bromo-2-methylbutane. We treat that with sodium methoxide in ethanol, and we either make the alkene on the left or the alkene on the right. So the alkene on the left is made by pulling off the proton from the secondary carbon that's next door to the carbon that bears the halogen. So that's the one to the bottom left. That will make the alkene that's shown. The alkene that's shown at the right, this one is made by taking a proton from either of the methyl groups that are attached to the carbon that bears the bromine. Either one of those will give that alkene. And so the tertiary, the trisubstitute alkene, that's a tertiary alkene, is the major product because it is the more stable, and that's called Zaitsev's rule. Make the more stable alkene, and this is the alkene that has more substitution. In the second reaction, you could either make the alkene that's the first one that's shown, 1-methylcyclopentene, or you can make the methylene cyclopentane at the right-hand side. The one on the left is more substituted, so that's the Zaitsev product. You predict that that's going to be the major product. And make the major product on these. Now and then I'll show you some examples of where you have to think about these, but in this particular case, you don't really have to think hard about which product is going to be major. You simply have to recognize which beta protons can be lost and which products can be made, and you make the more stable alkene. So there are two limiting mechanisms. That means these are the two extreme mechanisms for beta elimination. One is the E1 mechanism, and that's similar to the SN1 in that you lose the halide first, so you make a carbocation, and then the proton is lost from the carbocation to make the alkene. And E2 mechanism is where you lose the halogen and you lose the halide, you lose the hydrogen and you lose the halogen at the same time. So you're making and breaking all of the bonds at the same time, like the SN2 reaction. So let's talk about the E1 reaction first. We're going to break the carbon-halogen bond heterolytically, as we've done before, to make a carbocation and the bromide. Once we're at the carbocation stage, we don't need a very strong base to pull off the proton that's on a carbon next door. That is a beta proton. That's a proton on the beta carbon, which is a carbon next to the carbocation. Easy to take off so that we can leave the electrons there and make the pi bond. So that's step 2. Step 1, lose the halide to make a carbocation. Step 2, even a weak base can take the proton off the carbocation in order to make the alkene. So the E2 mechanism is a one-step reaction, as we've seen before for the SN2 reaction. And all of the bond making and bond breaking are going to occur at the same time. So in the scheme below, the ethoxide is pulling a proton off. The electrons that held a proton to that carbon are migrating over to make the pi bond. At the same time, The bromine is coming off as the bromide. All of those things are happening simultaneously to give the products. That's a one-step reaction. By the way, the energy diagram for that will be a one-hump reaction. The energy diagram for an E2 reaction, E1 reaction rather, will be a two-hump one with the carbocation intermediate in the middle. This is our summary of E1 and E2 reactions. Primary alkyl halides, E1 reaction doesn't occur. And recall, primary carbocations are very unstable, so they're very hard to get to, so we don't see them as intermediates. So for a primary alkyl halide, we'd have no elimination. E2 is the pathway, the only pathway that you could have for a primary alkyl halide. Secondary alkyl halide, and so these are reactions where you either make the carbocation in the E1 or do it all at the same time. That is, pull the proton off, make the pi bond, have the leaving group leave, all of those at the same time. If you're going to do an E2, you need a strong base. And that's generally true for any E2 reaction that you can do. You need a strong base in order to do an E2 reaction. And so the strong bases are those two oxygen anion bases. We're going to see nitrogen anion bases that we could use for E2. And mostly what we want is the anion, oxygen or nitrogen that are sterically hindered, and we want those so that they don't do the SN2 reaction, because that's a possibility as well. Tertiary alkyl halides, it's easy to make the carbocations from those because they're tertiary carbocations, and you don't need strong bases with those. You could have weak bases with E1. If you have a strong base, you can do an E2 reaction.